In this video, we're going to take a look at partial melting in two regions, continental rifts and mid-ocean ridges, and we're going to treat them together because they're somewhat similar. So let's first take a look at a cross-section of Earth. So here's the Earth's surface. Here's us standing on the surface, not to scale. And this is the core mantle boundary, which we will abbreviate as CMB. So down here we have a metallic core that is partially molten, mostly molten, and is very hot. That hot layer can heat up the material just above it and give rise to what we sometimes refer to as mantle plumes. And we'll just draw this upward moving material here. It's rising upward because it's hot. When we heat stuff, it expands. When it expands, it becomes buoyant. So if something is cold and then we heat it up, then it gets a little bit larger by the process of thermal expansion. So this hot material will rise and become buoyant, and you can think of this plume, this upward rising jet of material, as the upward limb of a convection cell. And once it hits the surface or comes close to the surface, it will cool off and then become dense and then sink. And we think that gives rise to volcanoes. Well, let's erase the chalkboard for a moment. That gives rise to what we might refer to as hotspot volcanoes, which are not the topic of this video here. We'll treat those in a different video. So let's take sort of a close-up view at what is going on in Earth's surface. So at a hotspot, we have a mantle plume coming up, and it's hot enough that even though we have this cold, rigid lithosphere that's blocking its way, we can still have enough heat that we have partial melting down here and enough partial melting that we can drive some volcanic activity. This is the volcanic activity that we would expect at some place like Hawaii or Yellowstone or the Azores. But there are other volcanic regions that actually dominate the surface of the Earth that have nothing to do with these mantle plumes, that instead have to do with the breakup of this lithosphere. So what happens if we take a bit of lithosphere and we break it and rip it apart? Well, if we break it and rip it apart, we might have something like this. Well, we'll start with some stretching. So maybe after stretching, this little bit of lithosphere would become thin before it would actually break. So here's where the break will occur. And as this material thins, we might have a depression at the surface, but then also we'll have this gap here where hotter mantle will be able to fill in that gap. And that thinning could lead to partial melting, which is what we're going to show now. So here we're showing, it doesn't really matter what kind of crust we have on top. We can be showing an example of a continental rift. So let's say we have some crustal material that's also being thinned, some sedimentary rocks that are filling in the basin here. It really doesn't matter what kind of overlying material we have. If we have lithosphere that is being thinned, then let's take a look at what happens in a cross-section of temperature versus pressure. If this is the mantle solid as here, and let's say we have a geotherm that looks something like this, maybe the initial geotherm is going to be such that it never crosses the solidus. So I'm going to draw it like this. So we have a fairly shallow slope here. That is where we have conductive cooling. So this is the lithosphere. That shallow slope defines the thermal lithosphere, where heat is transported by conduction. And then where we have this much steeper geotherm, we've drawn this so that pressure is increasing downwards and temperature to the right. So we have very little change in temperature. And in this cross-sectional view, we get a very steep curve in that part of the mantle that is part of the convective mantle, where mantle can flow. So the mantle is soft enough and hot enough that it can flow by convective currents here, but it hits this very stiff, cold, rocky lithosphere. That material is not taking part in the convective flow, and so this is basically what gives rise to the plates that are part of plate tectonics. Well, what if we begin to rip apart that lithosphere as we showed earlier? So we have a piece of lithosphere, we break it apart. Well, let's say we stretch it and we begin to thin it, or even even into the point where it literally breaks apart. And so we have thick lithosphere out here, but we have a full break here. That allows this hot material from the convective mantle to rise to shallower depths. So we could follow this curve. It should be pretty close to a straight line, really. If we thin the lithosphere, then we can have the convective mantle rise to a much shallower depths. So this is our initial lithosphere depth here. Let's call it L0. But then this dashed line here that I've just drawn in, that could be our lithosphere at some later time, T1. So it's a thinner lithosphere where L1 is less than L0. And what it does is it allows this very steep convective geotherm to reach to a much shallower depth than it would normally reach when that thick lithosphere is in place. And when that happens, now the geotherm is at a point where it is above the mantle solidus. This is the mantle solidus here. And now anywhere where the geotherm is higher than that solidus, we can have partial melting. So we have a region of partial melting here, and that region of partial melting might create enough melt that it can collect and buoyantly rise up to the surface and give us a volcano. So this is what is referred to as an adiabatic rise of the convective mantle, and that would lead to adiabatic partial melting. So these are the technical terms we give to it. An adiabatic rise, the convective mantle, is going to lead to adiabatic melting. And we will give a derivation of what we mean by adiabatic later to quantify this, but this basically means that a parcel of mantle will rise where there is no heat loss by conduction. So heat loss is not by conduction. Heat loss is only relative to, this is the mantle adiabat. This change in temperature with respect to pressure, that is the steep part of the convective of the geotherm. So we have a geotherm that looks like this. dt dp, when we write it with this equation here, which we'll explain in another video, describes that steep part of the curve. And that heat loss, or excuse me, the temperature loss is related to the thermal expansion coefficient and the volume of the material. So the heat that's being lost, the heat that's being lost is that as this material expands, it does work on its surroundings. So we have stuff going from high pressure to low pressure. As it goes from high pressure to low pressure, the material will expand. As it expands, it does work on its surroundings, and as it does so, the temperature decreases. There is no loss of heat by conduction because it's assumed that during convection, this material rises fast enough that there is no time for the very slow process of conduction to take place. So that's what we mean by an adiabatic rise. And this is a type of partial melting, coming back to the diagram we've just drawn earlier. If we come back to our TP plot, so temperature and pressure moving downwards, we have a geotherm that looks like this. And then we have a mantle solidus that looks like this. In this zone of partial melting here, this kind of adiabatically driven partial melting is something that would characterize continental rifts. So continental rifts, like the Rio Grande Rift in the southwest United States, or the Red Sea Rift near Africa, or mid-ocean ridges. So mid-ocean ridges are a place where the lithosphere is ripped completely apart. The lithosphere thickness goes almost to zero. Maybe just a couple of kilometers of crust above are acting rigidly and not taking part in a convective flow. So we have the lithosphere going to almost zero. We could start out perhaps with very thick lithosphere and have it thin to relatively shallow depths. And again, that thinning is what's driving partial melting in these kinds of tectonic settings. Continental rifts or the mid-ocean ridge system, which are another type of rift.